crazy. So many more people come. I thought it'd be more actually. So 9 out of, I guess about 50%. Review day. I always get so hungry at the end of these days. Burns lots of calories. Does anybody, so today we're just going to go review for the test on Wednesday. Does anybody have any questions about anything? Similar test. The test is it's going to have more space. So here's the test that has more space on it. You can see, so that way, I mean, these are scrunched up, but so you have a lot more space to write on the test than I'm just going to do in the margins here. So you get an equation sheet and a periodic table. So all the equations. So the periodic table and an equation sheet and constants. And believe whatever you need, and you can always ask for more during the test if you feel like you need more. Any questions? Okay, so rate of diffusion of oxygen to an unknown gas is 0.935. What's the other gas? So it's the square root. So the rate of A to the rate of B, this is equal to the square root of molecular weight of B over the molecular weight of A. So this is 0.935 equals the square root of, so it'll be oxygen, so it'll be unknown over 32. I'm actually curious to see what it is. It's going to be A or D, I think. I'm going to go ahead and calculate it out. I guess it'll be less than that. 5 squared times 32. And it's 28. So how you do this, you solve for this, is you square both sides. So square both sides, and then multiply by 32. It's 28. It's nitrogen. So you get how to do this. This is the Graham's law of diffusion. Rate of A over rate of B is equal to the molecular weight of B over the molecular weight of A. So given 0.953 oxygen to an unknown gas. So since it's oxygen to this unknown gas, so that means oxygen is A, unknown gas is B. Okay, so diffusion of oxygen to an unknown gas. Okay. So then you have so you flip it that way.
Oxygen is O2.
Yeah. Yeah, O2, 16 times 2, 32.
Yeah. And nitrogen is 2.
Yeah, 28, 14 times 2. And the answers are also on the bottom here. So, questions? How to do that? Okay. Root mean squared velocity. So the URMS, you're given this 3RT over the molecular weight. Even in the sheet it says molecular weight in kilograms. So it's the square root of 3R is 8.314. Temperature 298 Kelvin. All over nitrogen 0.028 kilograms. I'm not going to put all the units on there. Did you want me to throw that in the calculator, or is that good enough? Raise your hand if you want me to put that in the calculator. Okay. Do you want a picture of the calculator?
Wasn't the bottom of 3RT?
That's my italics M. And give you the equation as well. I even put M as molecular weight in kilogram. Okay, so 3 times 8.314 times 298. And 298 is 25 degrees in Kelvin. I'm getting some huge answer. Wait a second. Oh, I know what I'm doing wrong. Too many zeros. There we go. 515. You guys wanted the calculator too, right? There's the calculator. Answer there. But anyways, questions how to do this one. This one you just apply the RMS equation, which is given to you, and the R you use is 8.314, temperature in kelvins, mass in kilograms. Put it in square root. Questions on how to do this? So, using the following equation for the question of octane, calculate here reaction for 100 grams of octane. The molar mass of octane is 114.33 grams per mole. So, it's just by ratio. So, this dimensional analysis. So 100 grams of octane, mole octane to 114.33 grams octane. And minus 11018 kilojoules to 2 mole octane. Can you see that? I guess you can't. Okay. All right. I'm just doing OC. Oh, jeez. So 100 grams of octane, mole of octane to 114.33 grams right there. And the last step, this negative 11,018 kilojoules, that's from oh, this is all positive. Oh, it should be negative. But this here, this value for the heat of reaction, but there's a 2 here for the octane. So that's why I put the ratio of 2 moles octane. So, and whatever that is. Questions with the setup? What is the answer? So 9673. What's this one here? Do you guys want the photos of that? Question.
Yeah, I keep getting that it's
I think get the divided by 2.
Oh, I forgot to divide by 2?
Yeah.
Oh, shoot. I even put it right there. You're right. Glad I'm not taking the test. That was a dumb mistake. I even wrote it on the board. Oh well. There we go. Cover that up. So, questions with this? The old put the wrong numbers in the calculator trick. A compound is found to be 30.45% nitrogen and 69.55 oxygen by mass. If 1.63 grams of this compound occupy 389 milliliters at 0 degrees Celsius and 755 millimercury, what is the molecular formula of the compound? Oh god, it's going to be a long one. Okay, so this is the percent stuff, so 0.45 grams nitrogen, 69.55 grams oxygen times mole nitrogen to 14 grams nitrogen times mole oxygen to 16 grams oxygen. Okay. Two point 175, 0.175, 69.55 divided by 16. 4.346. So divide both sides by 2.175, and we get 1 there, and 2 there. So this means this is a NO2 compound. So we have an NO2 compound. Then we have to figure out the number of moles from this. So we figure out the ratio is 1 mole nitrogen to 2 moles oxygen. Then now 1.63 occupies that space. So we have to figure out the molecular mass. And to do that, we figure out the number of moles. So PV equals nRT, which implies N is equal to PV over RT, which is 775 millimeters of mercury times the atmosphere over 760. Mercury volume is 39 milliliters, 0.389 liters over R, 0.08206 liter atmosphere mole Kelvin. 0 degrees Celsius, 273.15 Kelvin. Put that in. 775 divided by 760 times 389, 5.08206. 273.15, and our N is 0.0177 moles, and if we have 1.63 grams divided by 0.01177 moles, 1.63 divided by answer, we get 92 grams per mole. So where do we go from here? NO2 is 14 plus 16 times 2. So 92 plus 2, this is 46 grams per mole. So if NO2 is 46 grams per mole and our molecular weight is 92, that means we have 2 units of the NO2. So that means we have N2O4. Does that make sense? Okay, I'll re-explain it. So that's N2O4. It's this one here. Okay. All right. I jumble up all the stuff. A compound is found to be 30.5% nitrogen and 69.55% oxygen by mass. If 1.63 grams of this compound occupies this stuff, what's the molecular formula of the compound? The first thing we have to do is figure out the ratio of the atoms. So we have the 30.45% multiplied by 100, 30.45 grams of nitrogen, convert to moles, 69 grams oxygen, convert to moles, and we get 2.175 moles nitrogen to 4.346 moles oxygen. Divide both by 2.175, and we get a 1 to 2 molar ratio. So it means we have nitrogen dioxide as the empirical formula, so the lowest ratio formula. And then now we got to figure out what the molecular weight is. So we're given that we have 1.63 grams of this. So using the ideal gas law, we calculate out we have 0.0177 moles. So 1.63 divided by the number of moles gives us 92 grams per mole. So in this NO2 is, that unit is 46 grams per mole. And if we have 92 grams per mole, that's 2 of those units. So 2 times NO2 is N2O4. So, does that make sense? Mm-hmm. Questions with how to do this? That's a horrible one. Whew. Man. The following reaction used to generate hydrogen gas in the laboratory. If 342 milliliters of gas is collected at 25 degrees Celsius, total pressure of 745 millimeters of mercury, what mass of hydrogen is produced? Okay. All right, so let's do picture time. So we're going to have, so it'll be something like this, where we have stuff in water, and in here we have, so this is H2O, so we have 25 degrees Celsius equals 298 Kelvin, 745 millimeters of mercury, and volume is 243 milliliters. Okay. So the mass of hydrogen. So grams hydrogen is our unknown. So we're looking for mass of hydrogen, and in here we're going to have H2, and can you, I guess you can't see that, shoot. Lots of colors. Okay, so we have some sort of reaction vessel on this, put in an upside down piece of glass on water. 298 Kelvin, 745 millimeters of mercury, 243 milliliters volume of this gas. What is the mass of hydrogen? You have to know that this mixture contains both water and hydrogen. So our total pressure is the pressure of the hydrogen plus the pressure of the water. So 745 equals pressure of the hydrogen plus the water pressure, and 25 degrees is 23.78. And we don't have that many digits. But so implies pressure of hydrogen is 745 minus 24 equals 721 millimeters of mercury, and the same mass PV equals nRT. So we're looking for mass and figure out mass. We need a number of moles. PV equals nRT. So this implies again N is PV over RT. 721. Volume is 3 liters. 0.86. It's 298. Okay. So 721 76 times 0.243 0.08206 by 298. This equals 0.00943 moles of hydrogen. Then we multiply that by 2 grams hydrogen per mole hydrogen. And then that's 0.0189 grams hydrogen. Which is so okay. So recap with this one. So magnesium plus hydrochloric acid makes magnesium chloride and hydrogen, and we carry this reaction out at 25 degrees Celsius. Pressure of and the ambient pressure is 745 millimeters of mercury, and volume 243 milliliters. So, what's the mass of hydrogen? So here are the conditions, and there's a mixture of hydrogen and water. So we have to subtract the vapor pressure of water, which is given to us right there. So step 1, subtract the vapor pressure of water, get the partial pressure of hydrogen to be 721 millimeters of mercury. Solve for moles with ideal gas law, and then when we get the moles, we multiply 2 grams hydrogen per mole hydrogen, and then we get 0.019. Question?
The 2 grams of hydrogen. Okay.
Yeah.
I'm just wondering the 2 grams. Oh.
I mean, I know it's
Yeah.
up there, hydrogen. It would be 2.016.
Yeah. Sorry.
That's no need to apologize. Other questions? Nope. Okay. Oh man, a lot of mole stuff. What mass of NO2 is in a 13-liter tank at 4.58 atmospheres and 385 kelvins? All right. So how are we going to figure out mass? We get the number of moles, N, NO2, and then multiply by 46. I just know 46 because we just did that one, right? NO2 is 46 grams per mole. So we just calculated that before. So I got to figure out the number of moles. So PV equals nRT, which N is PV over RT. So we have 4.58 atmospheres. Volume 13 liters, 0.08. Oh, jeez. 0.08206 liter atmosphere mole Kelvin. 385 Kelvin. So this is 1.88 moles NO2. Then we multiply by 46. We get 86.7 grams NO2. Which is D. Okay. Recap for this one. What mass nitrogen dioxide is contained in a 13-liter tank at 4.58 atmospheres, 385 Kelvin? So what we got to do is got to figure out the number of moles of NO2, then multiply by the molecular weight. So molecular weight's 46. Then we got to figure out what N is. So solve for N, then it's PV over RT. Pressure, volume over RT. Plug it in, get the number of moles. Multiply by 46. We get 86.7. Questions with that one? All right, time to switch it up. Calculate temperature in Kelvin of 2.2 moles of gas occupying 3.5 liters at 3.3 atmospheres. So PV equals nRT, which implies temperature is PV over nR. Finally, something different. Pressure is 3.3, 3.5 atm liters. N is 2.2 moles. 0.08206 liter atmosphere mole Kelvin. Okay. 3.3 times 3.5 divided by 2.2 divided by 0.08206. We're getting 64 Kelvin. So recap for this one, looking for temperature. So calculate temperature. So use the ideal gas law. Instead, solve for temperature. Temperature is pressure times volume over number of moles times gas law constant. Plug in those numbers, get 64. Questions with this one? All right, so I guess that's done for the gas laws. I'll stick with blue. I like blue. Wavelength is green. So wavelength 25 nanometers. What's the frequency? This is the speed of light is the lambda times the frequency. So implies the frequency is speed of light over wavelength. 3 times 10 to the 8 meters per second. All over 525 times 10 to the minus 9 meters. Okay, 5.71 times 10 to the 14th inverse seconds. I'll go ahead and take a picture of this. Well, it's weird doing all these problems staring at my iPad. I feel like I'm like chewing with my mouth open. Hopefully I'm not being too rude to you guys. Okay. So this problem is, what is the frequency for this wavelength of light? So 525 nanometers, what's the frequency? So speed of light is the wavelength times the frequency, which implies the frequency is the speed of light divided by the wavelength. Put in the numbers, and out pops the frequency. So 5.71 times 10 to the 14th meters per second. I'm going to go ahead and put that there just to show you can quickly put in your calculator that way. But questions with this one? Okay. Use standard reaction enthalpies to determine the delta H reaction for this reaction. Okay, so we have 2 sulfurs plus 3 O2s makes 2 SO3s. Okay, so when we look at this, this is Hess's law, if you remember talking about Hess's law. And you want this reaction. I'm going to call this H1 and H2. So we want that reaction, and the logic is to make sure, start off by putting the reactants on one side and the products on the other. So this reaction here we're going to flip because sulfur and oxygen are reactants and they're products here. So we need to flip this one here. We leave it alone because SO3 is a product and SO3 is a product and the reaction that we want. So you guys understand that logic? Okay. So let's go ahead and flip them, or flip the first one. So S plus O2 makes SO2, and this is minus H1. Then we have 2SO2 plus O2 makes 2SO3. This is H2. And the way I see it, and we want 2S plus 3O2 yielding 2SO3. That's what we want. So how do we get there? Right away I see we have two SO2s over here, so I think we're going to have to multiply this one by 2. That's my initial gut feeling. And then if I want 2s, I would have to multiply this by 2, that would have by 2, and then add it up, that would make 3. And then we get rid of the SO2s. So I'm going to go ahead then and multiply this whole thing by 2, like so. And as promised, the SO2s cancel. And then the 2 plus 1 equals 3 O2s. So right here. So we are left with what we want. And the delta H is going to be minus 2H1 plus H2, which is minus 2 times 296.8 plus a minus 197.8. I'm getting minus 791.4 joules per mole. Yep, right there. Section D. Okay. So recap with this one. We want to figure out what this is. The delta H for this, but we know these two things. So we look at this, and we got to decide which way to put the equations. This first one here, you know you're going to flip it because S solid and O2 gas are reactants and their products here. So we're going to make sure that they're on the correct side. So we're going to flip this and turn that delta H minus 1. And this one here, SO3 is a product. That's a product. We keep it like that. Also, O2 is a reactant, so we keep it there like that. So then we got to figure out what to multiply everything by. To get rid of the SO2 intermediates, you can multiply it by 2, or you can see that you need to have 2 sulfurs, so you multiply the top one by 2. Either way, you want to look at the logic. Both works out. Multiplying the top one by 2 and adding together, we get the equation that we need. And so then it's the opposite of 2 times the first enthalpy plus the second enthalpy. There's the first enthalpy, second enthalpy. Put them together, and we get minus 791.4. Questions with this one? I like the Hess's law. Students usually don't like it. So, which of these gases has the largest molar mass? So the bigger molar masses have a more narrow distribution, and the lighter ones have a broader distribution. So A is the lightest and D is the heaviest. So in this case here, it's D. Did you want me to explain that more, or is that good enough for you guys? No? Feedback's good? Any questions with that? Need more explanation? Nope? Okay. That's D. Okay. Use the enthalpy of formation to configure out the heat of reaction. So, okay. So the delta H reaction, which is given, is the sum of the N of products, H of products, minus the sum of N reactants, H reactants. So we apply this. Delta H reaction is going to be So 2 HHCl plus 2, I should say heat of formation of sulfuric acid minus 2H SO2Cl2 plus 2 H2O. So then we just plug in the numbers. Equals 2HHCl 2 times minus 92. Oh, I don't need the 2 here. I'm sorry. No 2 there. Plus H2SO4 minus 4. Minus 2 SO2Cl2. 6. So just taking the numbers from the chart and bringing them over, and then we have to put it in the calculator. Positive 30.
Section 2, I think. SO2 CL2.
Oh, I put a 2 there?
Yeah.
Oh, crap. No 2 there. You're right. I'm too liberal with my 2s. There we go, minus 62. So that would be, it's 11A. 11 is A. There we go. Questions with this one? Okay, so recap here. Delta H reaction is, and this is given, the sum of the number of moles of products, enthalpy of the products, minus this number of moles of reactants, enthalpy of reactants. Applying that to this equation, we have the products, HCl and sulfuric acid, so 2 HCl's minus SO2Cl2 and 2 waters. Put the numbers in, get that. That's 2 mistakes. I need to eat some candy or something like that. Guess I didn't get enough sugar for lunch. All right. Question on that one? Okay, so number 12. I think I'll do this the easy way. There's 2 ways to do it. There's a hard way and the easy way. I'll pick the easy way. The Rydberg equation, the delta E is the Rydberg constant 1 over n final squared minus 1 over n initial squared. So the final 4d to 2p. So this is going to be the minus the Rydberg 1 over 2 squared minus 1 over 4 squared. And then, so this is, so it's 1/4 minus 1/16. So this is going to be 3/16 Rydberg minus R infinity 3/16. So is it just 3 divided by 16 times 1.017? I think this is the easy way. Yeah, then you put this in with this Rydberg constant, and you get 0.02056,875, and then you have to invert that inverse, and you get 486 nanometers. So that's one way to do it. So that's number one. I'll show you if you want to do the long way. The long way is when you have the delta E, go here, the minus Rydberg 3/16. And if you put in the Rydberg constant to be minus 2.18 times 10 to the 18 minus 18 joules times 3/16. So this is equal to 4.09 times 10 minus 19 joules. So energy is H nu is Hc over lambda, which implies wavelength is Hc over E. 6.626 times 10 minus 34 joule seconds times 3 times 10 to the 8th meters per second, all over 4.09 times 10 minus 19 joules. So I can do it this way. 6.626 4 3E8 Oh wait. Let's use the answer. And this equals 486 times 10 to the minus 7 meters equals 486. So two ways to do it, give the same answer. So let me explain the easy way. And there is a problem just like this on the test. You're probably like, the easy way was way faster, but we've never seen that before. Okay, so going from a 40 to a 2p. What's the wavelength of light emitted? You're given the Rydberg equation that's given on the sheet. And I give you a Rydberg constant. There's also this constant here. Applying the delta E, it's the energy is 3/16 Rydberg. It's the 1 1 over 2 squared minus 1 over 4 squared, so that's a fourth minus 16th. So a quarter is 4 sixteenths. So 4 sixteenths minus 1 16th is 3 sixteenths. So 3 sixteenths times the Rydberg constant is the energy. If you use this one here, the top one there, the 1 times 10 to the minus 2, you throw this in, you get this number, and if you invert it, then you get the answer. So that's the fast way to do it. The way that I've been teaching you, the long way to do it, is, well, the energy loss of the electron is energy gained by the photon. So the energy gain of the photon is 4.09 times 10 to the minus 19 joules. And using this equation, we can solve for, so energy is Planck's constant times the frequency, which also equals Planck constant times the speed of light divided by the wavelength, which means wavelength is Planck's constant times speed of light over the energy of the photon. So plug it in, and then we get 46 nanometers. So, like I said, there is a problem just like this on the test. Whichever way you want to do it, if you want to do it the fast way using the Rydberg constant, you just have to remember to invert it. You do it. Question?
What is the, like, how do you then invert
1 divided by the answer.
1 divided by 6? Oh, okay.
Yeah. Inverse. Divided by the answer, or 1 over 0.000205 6 8 7 5 equals 46. Like that. It's also the -1 button. So you just press the -1 button, it'll do it. Questions with this one? I'll go to black. How many photons are contained in a yellow burst of light at 589 nanometers from a sodium lamp that has 609 kilojoules of energy? It's a pretty big burst. Okay. So the number of photons is going to be the total energy divided by the energy per photon. So we did cover this in class. This is considered to be science common sense. So kind of like if I have $20, how many 50-cent chocolate bars can I buy with $20? It's the total amount of money divided by the cost per item. So if I have $20 divided by 50 cents, half a dollar, that means I can buy 40 candy bars with $20, right? So instead of buying candy bars or something else, we're going to have, instead of money, we're having photons, and instead of having energy, and then energy per photon will give us the total number. So kind of the same idea like that. And the total energy is given to us 609 times 10 to the third joules. And then energy per photon, I guess I'm out of space. And 589 nanometers equals h nu equals hc over lambda. So we have, so this we have to put there. 626 times 10 to the minus 34 joule seconds. 3 times 78. Now I feel so much better after eating that chocolate. Whew. M&M saved my life again. 589 times 10 minus 9 meters. So plugging that all in. 609,000 times 589E minus 9 plus 6.626 plus 34 divided by 3. And I'm getting 1.8 times 10 to the 24 photons. Okay, recap with this one. And I'm going to pick up this pace. How many photons are in this 609 kilojoules burst of light? We're given the wavelength of the light, so the number of photons is the total amount of energy divided by the energy per photon. We're given the total amount of energy. Make sure you multiply it by 1,000 for kilojoules. And then the energy per photon is hc over lambda. Put that in, and you get 1.8 times 10 to the 24 photons. It's like 2 moles-ish. Questions with this? All right. Wavelength of light. I might, in the interest of time, I might use the fast equation. That's raise your hand if you want me to do this the long way. Okay, fast equation. So minus Rydberg 1 over n final squared minus 1 over n initial squared. And it's that transition to n equals 1 to n equals 3 in the hydrogen atom. Oh, so that's an absorption. Okay. So Rydberg 1 over 1 minus 1 over 3 squared equals 9/9 minus 8, or minus 1/9 is 8/9. 8/9 Rydberg equals 8/9, and the equation is 1.097 times 10 to the minus 2. All right. I'll go ahead and take the picture of this so you can. So that's how you do the inverse. You can do answer to the -1 to the -1 power, or you can just type 1 divided by that whole string. So, question, okay, well, this one here, wavelength of light from n equals 1 and n equals 3. So it's 1 over the n squared, so it's 8/9 Rydberg. And then you can do it the long way like I did before, or this one using this value of the Rydberg constant. So whichever way you prefer. I'm just doing it this way now because it's faster. So, questions with this one? Much like the last one, the one or two questions before. Okay, de Broglie wavelength. You're given that lambda d is h over mass times velocity, and I think you have a question like this in the test, and something that's confusing. This is the minus 31 kilograms. I even wrote that out because I didn't want to confuse you with the grams. So the BH 6.626 times 10 to the minus 34 joules second divided by 9.11 times 10 to the minus 31 kilograms, 3.66 times 10 to the 6 meters per second. So you get a question like this in the test, and you see after the grams is written in kilograms. That's not me trying to mess with you. I'm trying to help you. So you have to use the kilogram answer. I'm getting something close to 1.99 times 10, oh geez, times 10 to the minus 10 meters. Yeah, oh, there you go. Like so. So this one here, and you're given the equation. Planck's constant over the momentum. And I even put momentum as mass times velocity. So Planck's constant, mass is going to be in kilograms, and speed already given, just put it in. And it'll be typed as in grams. I'll write it by hand in kilograms. So if you recognize my handwriting, use my number. Questions with this one, though? Determine the longest wavelength of light required to remove an electron from the sample potassium metal. The binding energy for electron potassium is 1.76 times 10 to the third kilojoules per mole. So this is per mole. So which means you have a piece of potassium and you're shooting light at it and electrons are coming off. And this is 1.76 times 10 to the third kilojoules per mole. And then, actually I should write it this way. Kilojoules per mole times atom K. So listen. So mole is going to be in the top. Mole K over 6.02 times 10 to the 23rd atoms potassium. So we have to change kilojoules per mole to energy per atom. So 1.76, and that's 1,000 kilojoules. So this is 1,000,000 joules. So that's 1,000,000. So it's 1.76 million joules, because it's 1,000 kilojoules. Kilo is 1,000. Divided by Avogadro's number, and we get 2.92 times 10 to the minus 18 joules. So what is this? This here is your energy or your photon. So E equals h nu is equal to hc over lambda, which implies wavelength is hc over E. We plug that E in there. 626 times 10 to the minus 34 times 3 times 10 to the 8th all over 2.92 times 10 to the minus 18. Okay, I'll be fast. 6.626 E minus 34 times 3 e 8 divided by second answer. And this is 68 nanometers. And which is right there. All right, so tricky part of this one is you're given energy in kilojoules per mole. So convert kilojoules per mole to divide by Avogadro's number to get the energy of the photon for each atom. So the photon only works on one atom at a time. So our energy is 2.9 times 10 to the minus 18 joules. And then you can solve for the wavelength using that energy, and we get 68 nanometers. Questions with this one? I got 9 minutes to go through. Come on, zoom out. 3 more, okay. A constant pressure combustion of 15 grams of ethane releases 777 kilojoules of heat. What is the delta H for the reaction there? So, gotta do good old dimensional analysis here. So, 15 grams ethane. So, mole C2H6. Okay, 12 times 2 plus 6, 24, that's 30 grams. C2H6, that's just the molecular weight, times 2, I'm getting the right units, so no, I'm doing this wrong. Okay, I am doing this wrong. It's just like we did in lab today. Okay, so 777 kilojoules per 15 grams C2H6 times mole. Oh yeah, that's I got it backwards. 30 grams C2H6 2 mole C2H6, and then we have 2 mole C2H6 2 mole reaction. So if 15 grams releases this much, so we got to figure out how it is in moles. Also, we multiply it by 2, essentially. So that, and then we multiply it by 2 again because there's 2 moles of ethane per reaction. And not only that, it's a negative direction. It's releases. This releases means the negative. So it's just 777 times 4 for this. So whatever that is. So it's B. I know I kind of jumbled up with the discussion there. Okay, so 15 grams of this releases 777 kilojoules. So that's what we're at here. So that's the ratio. This produces 15. The 15 grams produces this. And what is that per mole? That's a half a mole. So per mole C2H6, it's twice that for this. And then, but we also have 2 moles of C2H6 for this entire reaction. So we have to multiply by the 2 there, and then to get the proper answer. So, and those of you who just had me in lab, this is pretty much what we just did in lab today as well. Questions with this? Okay. Okay, this is the Q is heat capacity change in temperature instead of the specific heat capacity. All right, so 2.06 grams of titanium is burned. Temperature change is that. The calorimeter is this. What is the energy per kilojoules per mole? So the heat here is this the heat capacity change in temperature. Heat capacity is 9.84 kilojoules per Kelvin or degree Celsius. I'll just put degree Celsius. Kelvin and degree Celsius are the same units. Delta T 91.6 minus 25. Final minus initial. Okay, 91.6 minus 25. That times 9.84. And we get minus 655.3 kilojoules. And this is per 2.06 grams titanium. So now we have minus the minus I'm getting from the fact that it's the energy is going up in the bomb calorimeter, which means that the reaction is exothermic. I guess strictly speaking here, I don't need the minus sign there, but the minus sign now comes out 0.3 kilojoules per 2.06 grams titanium times how many? Titanium is 47.87. 7.87 grams titanium per mole titanium. So answer divided by 2.06 times 47.87, and that is minus 15229 kilojoules per mole. So it's this one here. Times 74 kilojoules per mole. So like so. So again, this is much like we just did in lab, except instead of using water, we have just a plain old heat capacity. So heat is heat capacity times change in temperature. We get the heat of 2.06 grams. We get 655.3 kilojoules of heat evolved from that reaction. So then by dimensional analysis and applying the negative number because it's leaving the titanium, it's exothermic, it's leaving the heat. So divide by the mass times the molecular mass of titanium, we get minus 15,000 kilojoules as shown right there. Questions with this one? Look like I'm losing you guys. Okay. Which of the following sets contain an error? If n is 1, L has to be 0, then M epsilon has to be there. That's good. If n equals 2, L can be 1, epsilon can be minus 1, 0, 1. That's good. N is 4, L has to be 1, 2, or 3. 2 is fine. If L is 2, M sub L can be minus 2, minus 1, 0, 1, or 2. That's fine. If N is 3, L can be 0, 1, or 2. It cannot be 3. That one's wrong. So it's D is wrong. N is 3, L can be 0, 1, or 2. If L is 0, M sub L is 0. So this one's good. So D is the one that's wrong. That's my shut up alarm. I'm gonna finish the last one here. Determine the final temperature of a gold nugget that starts at 398 Kelvin and loses 4.85 kilojoules of heat to a snowbank. So Q is MCS delta T. And what's the final temperature? So our heat, so MCS final minus T initial. So this means then that Q equals, or we should back up. Q over MCS is equal to delta T. So solving for delta T is TF minus TI, or the final temperature is heat over mass times the heat capacity plus the initial temperature. So Q is 4850 joules. Mass is 376 grams. Specific capacity 0.128 joules per gram degree Celsius, plus it's the other way. Oh well. All right. I got this the other way around. It's going to be Ti minus that. What am I doing? Oh, so because this is a negative direction, I see. Plus or minus that. Okay. All right. And what is Ti? 398. Okay, well, let me explain this one. Our heat flow is mass times heat capacity change in temperature, and we're losing heat, so that's why it's a negative direction. And solve for delta T. Delta T is the heat over mass times specific heat capacity. Delta T is final minus initial, so that means the final is this heat flow plus the initial temperature. Temperature is 398, and here's the heat flow. Heat divided by the mass and then the specific heat capacity. That will, you take that number, subtract it from 398, and you'll get the answer. I can do my calculator real fast. I mean, 297. 297 Kelvin. Okay. Alrighty. Sorry to keep you after. And I will stop recording.